So let's go to the content of this to understand exact application. So I discussed about this in the beginning of the matrices itself. So what is it? If there is a linear equation, if there is a pair of linear equation, definitely when you solve the linear equation, there are three possibilities. One possibility is it can have a unique solution. It can have a very unique solution. Okay, that is one possibility. Can you tell me the remaining two possibilities? It may have a no solution or a zero solution. The number of solution is zero. Or it can have more than one solution. Most of the cases, infinite solution. Okay. So whenever a system of linear equations have one or more solution, that is these two conditions, we say the system of linear equation is consistent. Okay. And if you are getting no solution at all, they represent what I told you. They represent parallel line, and there's also another way to call them, that is inconsistent set of solution. Why inconsistent? Why consistent? There's a very simple logic, but which is beyond the scope of your syllabus. Let me not go there. Okay. So in any other class where we have enough time to discuss this, we can discuss. Right now, just try to understand if there is one solution or more than one solution, we call it as a consistent system of linear equation. And if there is no solution, we call it as inconsistent system of linear equation. Okay, so why are we discussing this? Very important question. If somebody is curious. Okay, I'll tell you. So if you have a linear equations like this, let me take a simple one example. Maybe if you have a1x plus b1y plus c1z is equal to d1, a2x b2y c2z is equal to d2, and see, if it is a two variable, it's always easy for us to solve linearly, no doubt in that. But if there are more than two variables like x, y, z, it becomes tedious. That is where we bring matrix and determinants so that we can make the problem easy to solve them. So I can represent this set of linear equation in the form of a matrix product. Okay. That is A1, A2, A3, B1, B2, B3, C1, C2, C3 multiplied with which matrix now? It has to be a variable matrix X, Y, Z. And this should be equal to what? D1 exactly, D2, D3. Are you understanding? Now, let me represent this as A. Let me represent this as X. This is equal to D. Now, if I want to find the values of X, D, Y, and D, I just have to multiply this with what? If I want only X, I can say I'll multiply A inverse to entire equation. Okay. So I end up with A inverse into D. Okay. So, and this will become I identity matrix X into A inverse D. So finally, what is the value of X? It will be A inverse into D. So this is the method where we are going to use the method of inverse of a function, inverse of a determinant or a matrix to get the solution of a linear equation. So this will definitely give you a 1 cross 3 matrix, so which can be used compared with maybe it's some value, say alpha 1, alpha 2, alpha 3. Directly I can say X is alpha 1, Y is alpha 2, and this is alpha 3. This is the crux of this method. And for all this, we need to have what kind of system? It has to be consistent system. Okay. So that means how to check the consistency? We just have to find the determinant of this matrix. If the determinant of this matrix is not equal to 0, then it is consistent. If this determinant is equal to 0, then it is inconsistent. Then we cannot solve such questions. Simple as that. Hope this part is clear. Let's see some example. Yes. So let me reiterate all those points which we discussed here. If you want to solve a system of linear equations which more than 2 or even 2 variables or 3 variables of this format, we can represent them as a product of 2 matrices. Okay, with the constants here and the variables here and the final constants on the right side here. And I can express this as a matrix A into variable matrix X, which is equal to under constant matrix D. Okay, so with the help of inverse concept, I can multiply inverse of A on both the side. I end up with A inverse of A into X is equal to A inverse of D. And bringing the associative property, I can multiply A inverse of A together to get identity matrix and X. This is becoming A inverse of D. Identity matrix is nothing but what? We just multiply 0, 1, 1, 0, or if it is 3 cross 3 matrix, we are going to have a identity matrix with 1 on the diagonal side, right? So when you multiply identity matrix, you get the same matrix. So you can simply say X is equal to A inverse of D. So what is our process here? Finally, first we have to verify whether it is solvable or not by checking the inverse of a matrix. So a determinant of a matrix. If the determinant of a matrix is not 0, we can proceed further by saying inverse exists. Once the inverse exists is cleared, we will try to find the inverse of that with the variable matrix with the constant on the right hand side. So that itself will give you the variable matrix with the 3 or 2 variables. Shall we quickly check an example so that it is very clear for us with the example? Yes. Before that, yeah, so all these discussions has been there. You can quickly read them once. Okay, so the inverse of P exists, then A is a non-singular matrix. So multiplying exactly whatever is said, multiplying inverse on both sides, we end up with identity matrix and M. So finally finding the value of M is given like this. If it is a singular matrix, then what we are going to do? If it is a singular matrix, we have to calculate the adjoint of P. Okay, and yeah, so we don't have to worry about this if it is singular matrix right now because we only discuss non-singular matrix. Okay, so you can just read this content later. Let's move on to the solved examples quickly. Yes. So there is a set of linear equation. Definitely we can solve by solving normal method, right? But so normal we have multiple approaches. What is it? Elimination method, substitution method. How many of you recall cross multiplication method? Now we can use determinant method. This one more method. See, as we progress, we keep learning more and more methods. So this is fourth method, which is determinant method. In this method, what I'm going to do is first I'm going to establish the matrix with the coefficients of the variables. Right? What is that? So we have the coefficients 3, 4, 4, 5, and there are 2 variables only, x, y, which is equal to 2, 7. So let us take it as a, let's take it as x, let's take it as d. So if I want x now, what I should do, my concept simply says find the inverse of a and multiply with this matrix, right? How to find the inverse of the a? First you find the determinant of a, which is 3 5s are 15 minus 16, which is minus 1. Right? So determinant of a is minus 1. It's non-singular, so we can proceed further. Right? So what is adjoint of a? Adjoint of a is, so it is going to be 5 here, 3 here. This is minus 4, and minus 4. Transpose of that, right? So what is adjoint of A now? Adjoint of A is, I think transpose, yeah. So this will be 5, the minus 4. Okay, it will be minus 4, yeah, minus 4 and then 3, right? So what is our inverse? Our inverse is adjoint of this divided by minus 1, which will make it minus 5 plus 4 plus 4 minus 3, right? So we are going to multiply this with the given matrix. What is this constant matrix? So I'm going to multiply that minus 5 plus 4 plus 4 minus 3 into what do we have? 2 and 7. So if you multiply, what you get? This is equal to the variable x and y. So minus 5 into 2 is, I'll get, yes, just a second. So it's been multiplied here already. What is minus 5 into 2 is minus 10 plus 28, which will become 18. And 4 into 2, 8. 8 plus 21, which will be, sorry, 4 into 2 minus 21. It's going to be minus 13. So that will end up with x and y as 18 and minus 13. So that's how x is going to be plus 18, y is going to be minus 13. That will be our answer. So this may be simple if it is a 2 cross 2 matrix. It may be very complicated if it is a 3 cross 2 matrix. But simply by practicing, you can ace even it is 3 by 3 matrix as well. Okay. So let me take one last example. Maybe if there's a 3 cross 3 matrix, and then we can wind up this session. Yeah. See the process. We'll try to solve them here only. So first we'll establish the matrix. That is 2 minus 3. It has to be plus 4. This has to be 3. Okay, this is here given, right? We don't have to write them again. So just observe them. So we have space for the steps. So this is the matrix 2 minus 3 plus 4, 3, 1 minus 1, 4, 2 minus 3, and x, y, z. And our constants on the right side is 8, 3, 6. First, we have to find the determinant of that. That is 2 into minus 3 into 1 plus 2. Minus of minus 3 becomes plus 3. Minus 9 plus 4. And then 4 into 3 2s are 6 minus 4. So what are we getting here is 2 into minus 1 minus 2. And 3 into minus 5 minus 15. And we have 4 into 2, 8. So finally, when you solve this, we end up with minus 17 plus 8, which is actually minus 9, not equal to 0. So I have got to know the determinant of this. So what is my next step? My next step must be finding adjoint of A. Transpose of that will give you transpose of the cofactor matrix, right? What is the cofactor of this? So let me write cofactor of maybe A11. I'll write it here. Step by step we'll write. So it is plus indeed minus 3 plus 2, which is minus 1. A12 will be minus of minus 9 plus 4, which is plus 5. So I'll write it here directly, plus 5. And A13 will be again plus sign, 3 2s are 6 minus 4. Yes, 3 2s are 6 minus 4. What do we get? Tell me. Which is plus 2. This is 2. Similarly, A21. will be minus sign, minus into minus plus 9, minus 6, minus 8, right? Yeah, which is minus 1. I'll write it here. So A22 cofactor of this. So if we want to eliminate this row and this column, minus 6, minus 16. Am I right? Yeah, minus 6, minus 16, which is minus 22. I'll write it here. And A23. What do we have? A23 will be negative sign. After that, what do we have? 2 2s are 4, 4 plus 12, 16. Yes, minus 16. So let's quickly check the cofactor of this in the next slide instead of wasting our time by solving each and everything. Yeah. So here we are getting these values. Let me erase this. So adjoint has been found here. So minus 1, minus 5, 2, 1, 2, 16, and minus 2, 10, 1. We're dividing this by 9. After that, we're going to multiply with our constant values 8, 3, 6. So when you multiply them, these are all coming in fractions because the values are like that. When you solve this equation, it's very difficult to get the solution. First of all, it's a 3-variable linear equation, and all the solutions are coming in fraction. So this is the most better method than solving in any other format. Okay, because it's a 3-variable matrix method is very important, easy for us compared to any other method. Unless the solution is easy. Here the solution is also not easy, right? Try to remember whenever you come across solution of linear equations with 3 variables, there is a very easiest approach, that is inverse of inverse of a matrix method. Okay, if you come across any competitive exams, you can do this. Okay, that's all about determinants. So let's quickly have a summary of what we learned in the past 2 classes on determinants. Okay, yes.